Welcome to week 11, multivariate functions, extrema, and the Lagrange function. Let's begin with looking at what we've done in prior weeks with single variable functions. We learned that the extrema, maximum and minimum values, of a single variable function were at points where the slope of the derivative was 0. So you may remember a diagram we had on the board like this, right? And that would be the derivative, and the slope at these points would equal 0. So the process for finding those extrema points were find the derivative, and we use those derivative rules. We set it equal to 0, the derivative, and we solve for the variable. Solving for the variable would determine the x value of where the maximum or minimum points occurred, and then we could substitute that variable into the original function to determine what the value was of the function at those points. In week 10, we started looking at multivariate functions, functions that have more than one variable, and we determined that we could find partial derivatives, meaning derivatives with respect to each of the variables in a multivariable function. Just as we can find extrema, maximum and minimum points, of single variable functions, we can also determine those maximum and minimum points for multivariate functions. The starting off points are the same. We find partial derivatives for each variable using the derivative rules we've already learned and become comfortable with. Generally, in the examples we're going to use, we're going to end up with two linear partial derivatives. So we would have those, and we're going to set them equal to 0. So that's the same. We're going to solve for values of the variables. In our case, we're likely to have two variables in these multivariate functions, so we're going to be solving for the value of each of those. But because they are two partial derivatives, we're going to have to solve them using some techniques that we learned early on in the semester, because we're likely to have a set of linear equations that we're going to have to solve using either substitution, elimination, or everybody's favorite, graphing. Realistically, we're going to be solving them using elimination. Let's see how this works in practice. Let's look at question number 1, extrema of multivariate functions. So as I stated before, single variable functions, we were able to find extrema, both maximum and minimum values. And it's the same with multivariate functions. There are maximum and minimum points. And the same business concepts apply. Again, you want your costs minimized, you want your revenue and your profit maximized. So that has not changed, of course. The first step in finding extrema of multivariate functions is to find partial derivatives. And to know what kind of partial derivatives we need to be looking for, we need to look at the number of variables we have and what they are specifically. And in this case, we have an x and we have a y, and we have terms that contain x's, y's, and a combination of both. So you'll recall in the partial derivative lesson, our first partial derivative will be with respect to one of the variables. So let's pick x. When we take the derivative with respect to x, we consider every other variable constant. So the y will be considered a constant. So we're going to look through each term. We're going to determine what rule of taking derivatives we're going to be using, and whether we have the x variable in the term or not. So the first term, 2x squared, there is indeed an x. We need to take the derivative. We're using power rule, which we're going to remember is x to the n. Derivative is nx to the n minus 1, just to remind us. So the first term, derivative is 4x. Plus 3y squared, there's no x in there at all, so that's a constant. Derivative of a constant is 0. Minus 2xy. So this is where we have a combination of the two variables, and so the 2 is a constant, minus 2. The y is a constant, and so the derivative of the term is 2y, or minus 2y. And then we have plus 2x, so there is an x in there. We're going to be taking the derivative of that, and that is plus 2. Minus 126y, there's no x, that's considered a constant, so derivative 0, and plus 3800, constant, derivative is 0. So that is the first derivative with respect to x. Okay, so now we're going to take the first derivative with respect to y. We're going to do the same thing, looking at each term one by one, but now we're going to be taking the derivative with respect to the variable y, and the x variable will be considered a constant. So here we go again, 2x squared, there is no y, that means that the derivative is 0, plus 3y squared, there is a y of course, and the derivative of 3y squared will be 6y, minus 2xy. So we addressed that in the first derivative with respect to x, and we need to look at it again because it has an x and a y in it. This time the x is considered the constant, y being the variable, and the derivative of minus 2xy with respect to y is minus 2x. Plus 2x has no y, so the derivative there is 0. We consider that a constant. Minus 126y, the derivative is minus 126. And plus 3800 is still a constant, doesn't have an x or a y, derivative is 0. The best thing to do now, well, we're going to set them to 0, so set equal to 0. And while I'm doing that, I'm also going to line up the variables under each other, so we are making sure that we're working with the same variables. So you see how I'm writing minus 2x first, plus 6y under the minus 2y, and minus 126 here. Okay, just so the x's are lined up and the y's are lined up. So now we have two equations with two unknowns, and if we flash back to week 3, I think it was, we know how to address this, and now that skill we learned and practiced then is going to help support our understanding and ability to solve this question. So we can solve by elimination, substitution, or graphing. I'm going to suggest here that, like in many cases, elimination seems to be the best way to address this. So I'm going to say this is equation 1 and this is equation 2. And in order to do elimination, I'm looking at the coefficients or the numbers in front of the variables to see which ones are related. And in fact, the coefficients of x and y are both related quite well, but I'm going to choose to multiply equation 2 by 2. Okay, so minus 2 times 2 is minus 4x, plus 6y times 2 is plus 12y, and we have minus 126 times 2 is minus 252, and I'm going to add them together. I'm adding them together in order to eliminate one of the variables, and in this case we'll be eliminating the x, because 4x plus minus 4x gives us 0x. I'm going to write that just so we have a visual that we've addressed that. Minus 2y plus 12y, that's going to give us 10y. And here, plus 2 and minus 252 is going to give us minus 250, and that still all equals 0. So I'm going to go to the next page, and we'll see how we can solve it from there. We have 0 equals 10y minus 250. We add 250 to both sides because we're trying to isolate that variable. And so now we're going to divide both sides by 10 in order to have the value of 1y. And we see that y is equal to 25. Okay. Now we take that value of y, substitute it into either of the first partial derivatives, and solve for the x. For x minus 2 times 25 plus 2. So for x minus 50 plus 2, set that equal to 0. 0 equals 4x minus 48. Add 48 to both sides. Divide by 4 on both sides. We're going to have x equals to 12. Right now you're probably thinking to yourself, well, how do I know the values that we have found result in the cost being minimized? Or maybe you're not thinking that, but we do have to show proof that we've found minimum values. So the first thing we need to do is find the second derivatives of the two first derivatives we found. And I'm going to draw a little diagram to help visualize first and second derivatives. So if we have a function with two variables, we can find the derivative with respect to x, and we can find the derivative with respect to y. We just did that. Then we can find second derivatives with respect to x or with respect to y of the first derivative with respect to x. Again, we can find the second derivative y, so that's the second derivative with respect to y of the first derivative with respect to y, or we can find the second derivative with respect to x of the first derivative with respect to y. Looks like a little bit of a genetic diagram. So knowing that, we know that if we have two variables, we have two first partial derivatives and 4 second derivatives. And if we had 3 variables, we would have 3 first partial derivatives, and so on. You'll recall that these are our first derivatives, one with respect to x and one with respect to y. So I've written them here for us to continue. And now we're going to find the second derivative of the first derivative with respect to x again. Same process, really. We're going to be looking at each term. We have a 4x, a minus 2y, and a constant 2. We're going to take the derivative using the same derivative rules that we have come to know and use quite proficiently. So we look at the first term, 4x, the derivative is 4, minus 2y, there's no x in it, the derivative is 0, and 2, of course, the derivative is 0. Let's take the second derivative with respect to y of the first derivative with respect to x. So this is a little bit of a twist. We can do this. We're going to look at the first derivative with respect to x, and now we're going to keep the x term x variable constant, and we're going to be looking at the terms for occurrences of y. And in this case, we only have minus 2y, and so c of xy is minus 2. Okay? So now I'm going to take the second derivative with respect to y again of the first derivative with respect to y. And so the first term is 6y, the derivative of that is 6 minus 2x, x is a constant in this case, derivative is 0, minus 126, it's a constant, derivative is 0. If we are trying to determine if it is a maximum or minimum, these are the general conditions. If we have a second derivative that is greater than 0, we have a minimum value. We're looking for a minimum because we were trying to minimize costs. We see that xx and yy are both greater than 0, so that means we have found a minimum. We also have to complete the value of m, which really determines if you have an extrema at all or you have a saddle point, and this is determined through this equation. And we should say that we have 4 times 6 minus 2 all squared. So we're going to have minus 4. 24 minus 4 is 20. It's greater than 0. It means we have an extrema of some sort. But the double derivative xx and yy, they're the ones who determine whether we have a minimum or a maximum. So if the second derivative xx is greater than 0, we have a minimum. If the second derivative, I'm going to write it up here, if the second derivative is less than 0, then we would have a maximum. We're going to see that occur in other examples that we'll do. What do we do now to finish up this question, now that we've found the values of x and y that will minimize costs? We have proven or determined that those values in fact are values that minimize the cost. Our last step is really to determine what is that minimum cost at those values. And that's a simple substitution of those values into the original function, because that is our cost function. So we're going to solve c at 12 and 25. And everywhere we have an x, we're substituting 12. And everywhere we have a y, we're substituting 25. And when we use our order of operations correctly, by doing our exponents first, then our multiplication, then adding them all up, this value is going to equal 2,237. So that will be the minimum cost when you produce 12 units of electrical tape and 25 units of packing tape. Another application of partial derivatives is the use of the Lagrange function. The Lagrange function is used when you have a multivariable function and some type of constraint in the form of a constraint function, and you're trying to combine these together. The Lagrange function relies on the use of a multiplier, which looks like this, and it's called lambda, Greek letter. And this connector piece is kind of like Lego when you're trying to connect something bigger to something smaller, or one piece of something to another piece of something. And this lambda is allowing us to connect a function with a constraint. What is a constraint, you're probably asking? A constraint in a business setting would be a requirement to produce a certain amount of product given certain set of conditions. In order to use this application in our questions, we're going to have to be given information about what the constraint is affecting the business. And you'll see that in the example that we'll do. So the Lagrange function looks like this. F at x, y, lambda. So now we're introducing that third variable, or third piece of information. And the Lagrange function has the multivariable function minus lambda times that constraint function, which we're going to have to create from information given. The steps we take then are to find the first derivative of that function with respect to the x variable, the first derivative of that function with respect to the y variable, and then we'll be able to solve for values of x and y that will either maximize or minimize this business application depending on what we're asked for. How does a Lagrange function and the Lagrange multiplier actually work in reality? Here we have a question that reads, the total cost to produce X small first aid kits and Y large first aid kits is given by the function C at xy is equal to 2x squared plus 6y squared plus 4xy plus 10. Now we're becoming more comfortable with seeing two variables in a function, and we know how to find the derivative of a multivariable function. So we're comfortable with that. Now we've added this other layer, that this business has a constraint that we need to consider. And here, if we look at this next line, it says if a total of 10 kits must be made, that is your business constraint. So if 10 kits must be made, how should production be allocated so that the total cost is minimized? Allocation means how much of one product versus how much of another product. So in this case, it's small first aid kits and large first aid kits. So how many of each should be produced in order to minimize the cost? If we look at our Lagrange function, right, it has to look like this with our function minus lambda times the constraint function. So we're going to substitute the function that we have, and we're going to consider the constraint. So this idea that 10 kits must be made, we have small kits being represented by x, large kits being represented by y. Our constraint is going to look like this. The number of small kits plus the number of large kits must equal 10. For use in this Lagrange function, we have to represent the constraint function as equal to 0. So it's going to be 0 equals x plus y minus 10. Now we get to substitute the functions into the Lagrange function. So we have function x, y, and lambda is equal to 2x squared plus 6y squared plus 4xy plus 10, and then we have minus lambda times x plus y minus 10. Our next step would be to expand these brackets, but remember, we've got to apply that negative sign in front of the lambda to all the terms in the bracket. So let's simplify this first. It looks like we're repeating a lot of steps, but we have to be organized in how we do this in order not to make silly mistakes. Minus lambda x minus lambda y plus 10 lambda. Following the same methods that we used to find derivatives of multivariable functions in past examples, we're going to do the same with this Lagrange function. So we have 3 variables and 3 possible partial variables. So let's start with the first derivative with respect to x. We look at each term in the function and see which ones have an x in them anywhere. So 2x squared has an x. The derivative of 2x squared is 4x. Plus 6y squared does not have an x, so the derivative is 0. We consider y and lambda a constant in this case. Plus 4xy, it does have an x, and the derivative of 4xy is 4y. Plus 10, of course, that's a constant. The derivative is 0. Minus lambda x, so that has an x in it, and the derivative of minus lambda x is minus lambda. Minus lambda y has no x in it, so the derivative is 0. Plus 10 lambda, again, has no x in it. The derivative is 0 with respect to x. Now we look at the first derivative with respect to y. And we go through each term again. 2x squared, there's no y in it, so the derivative is 0. 6y squared, there is a y, and the derivative of 6y squared is 12y. Plus 4xy, the derivative with respect to y now is 4x. Plus 10, derivative is 0. Minus lambda x, derivative is 0 because there's no y in it. Minus lambda y, the derivative of that with respect to y is minus lambda. Plus 10 lambda, the derivative is 0. We can and should take the derivative of lambda here, because that is our third variable. And we can see that in the first few terms, 2x squared plus 6y squared plus 4xy plus 10, there's no lambda, so those are all derivatives are 0. Minus lambda x, so that's going to be minus x, minus lambda y will be minus y, plus 10 lambda, the derivative will be 10. What are our next steps? We had solved our partial derivatives in prior questions by using the process of elimination or substitution, knowing that we had 2 equations and 2 unknowns. In this case, we're going to take a little different path, and we're going to set the first derivatives equal to 0. And then we're going to add lambda to both sides so that we're going to get here lambda equals 4x plus 4y. And here lambda equals 4x plus 12y. So in any case of equality, which these are with the equal sign, we have lambda equals one set of terms, 4x plus 4y, and we have lambda equaling 4x plus 12y. So what if we put those together? If we know that 4x plus 4y equals lambda and 4x plus 12y equals lambda, then those two sets of terms must be equal to each other. So we have 4x plus 4y equal to 4x plus 12y. Here we just follow the math and solve for the variables. So we have 4x minus 4x on this side, and we have 12y minus 4y on this side. 0 equals 8y, so y equals 0. While this may look initially a little odd, it simply defines the way that you can minimize the cost in this situation. Given the constraint that x plus y must equal 10, where this is the number of small kits and y is the number of large kits, we substitute the value of y equals 0 into the constraint function. So we have x plus 0 equals 10, x must equal 10. And so in order to minimize the cost, given the constraint that this company must produce a total of at least 10 kits, the allocation should be 10 small first aid kits and no large first aid kits. To wrap up this question, we now have to substitute these values of x and y into that cost function that we started with way back when and determine what that minimum cost would be. And with one of the variables being 0, it certainly makes this a lot easier because this will be 0, this will be 0. So we have 2 times 10 squared plus 10. Following our order of operations rules, we have 10 squared is 100 times 2 is 200 plus 10 is 210. So the minimum cost with this production allocation will be $210. So that wraps up the mini lesson on extrema of multivariable functions and the additional application of the Lagrange function. There are more solved questions in other videos that I hope you'll follow along to practice and learn a bit more.